Welcome into kind of a special edition of class today. Sorry about the quick departure. My daughter was sick from daycare, had to watch it this afternoon, so wasn't able to make it live today. So I'm recording this video today. What we're going to do is just maybe a little review of what we talked about last Friday, and then we'll get into a couple example problems using some of the stuff that we've been talking about. We've been doing a lot of math lately, so I feel like maybe some example problems, some application problems, some reality might be good for us. So yeah, let's get right to it. The beauty of doing a video lecture, by the way, is that you can speed me up if you want to go to, 1.25x or 1.5x, that would be fine, probably better. And also, I'm going to get some example problems up here. You might have to copy them down if you're trying to take notes by hand. So you can pause the video. It's the beauty of doing this on YouTube or doing a video recording. So I'm going to put you over on the writing pad, and we'll go ahead and get started. Okay. So we should all be seeing the writing pad at this moment. I'm going to do a quick review of what we talked about on Friday and then get into some example problems. Two example problems, that is. Okay, last time we talked about thin composites, right? So we said if a composite is thin, which most of the time they are, right? When you manufacture these composites, they're made with like stacking layers of fabric that are quite thin on top of each other, resulting in like a thin structure generally, or even a tube itself is usually quite thin. If you're doing a filament winding, taking it off the mandrel tends to be quite thin, right? Um, so if a composite's thin, we say that it's in a condition of plane stress. Why does it keep jumping? In a condition of plane stress, right? So what that means is that there are some stresses that we say that this particular composite is not very good at holding. Specifically, that would be any stresses associated with the out of plane direction or the three direction here, right? So um, in our matrix of stresses, right, sigma 1 through sigma 6, that 6 by 1 matrix, we would then say that stresses 3, 4, and 5, which are sigma 3, 3, tau 2, 3, and tau 1, 3, are all equal to 0. So if we make that assumption, we can sort of shift our focus from a full like three-dimensional state of stress and strain to an in-plane state of stress and strain, where the in-plane dimensions are the dimensions of the thin composite. So we're going to shift our focus to an in-plane response. So again, going from this like full 3 by 3 condition where we have strain equals this huge 6 by 6 compliance matrix multiplied by this 6 by 1 stress vector, we're going to take our attention away from that 3D case, and we're going to look solely now at a reduced or a contracted in-plane compliance matrix, or Hooke's law in-plane, where we just have the in-plane strains, epsilon 1, epsilon 2, and gamma 6, which remember this is actually gamma 1, 2. And a new compliance matrix that has much fewer entries, and our stress vectors in the plane, right? Sigma 1, sigma 2, and sigma 6. We had some shorthand for this guy that made use of this like plane stress symbol in the lower right. Eventually, we're going to drop this notation. I think we're going to get to a point where we're only really talking about thin lamina in this class, and so I'll use this plane stress symbol for a little while, but eventually I'm going to drop it. And you'll just have to assume or know that I'm talking about like the two-dimensional case, right? So this is the strains in terms of stresses and compliance, and this would be that reversed where it's stresses in terms of strain and stiffness matrix Q. We've got this new letter for the stiffness matrix when it's a two-dimensional version, capital Q. Why that is, don't ask me. It's not my convention, but that's what we do. All right. So we have this new 3 by 3 in plane situation going on. And we can still execute transformations of stresses and strains from one coordinate system to another, except now we don't have to do that crazy 6 by 6 transformation matrix with all the M's and N's and P's that, was super fun for you guys in homework 5. Instead, we have a much simpler transformation where we're looking at just an in-plane rotation from, let's say, an XY coordinate system to a 1, 2 coordinate system for the stresses, and an XY to a 1, 2 for the strains. And so the situation you should be thinking of in your head is, okay, this is a thin unidirectional laminate. I got my fibers sort of running in this direction, which is the one direction. And maybe I have another coordinate system that's an XY coordinate system that's rotated from the 1, 2 coordinate system by an angle theta, which let's say that we know. And then I can do transformations according to these matrices here, where we have M's and N's in there, which represent cosine theta and sine theta. So this is just a change of basis. We've talked about this. You've seen this, and you've done this in a 3 by 3 form for the most recent homework. Okay? So that's about where we left off, and I thought it might be nice to actually do some real example problems given the information that we've had up to this point. So here's the first example I'm going to go through. This is actually straight from a final from the composites class in 2021. So this is from fall 2021. ME 429 is what the class used to be called. So this is right from a final. And so if you want some time to copy this down, feel free to pause the video. Otherwise, I'm just going to get right into it. Okay. So here we have a thin unidirectional lamina has principal coordinate material stiffness matrix Q as shown. So this is quite nice, right? The problem here is giving us the in-plane stiffness matrix Q. Normally, you'd have to know things. You'd have to find like E1, E2, nu 1, 2, and G1, 2 from Halpin psi. Use that to populate S, which remember looks something like 1 on E1, negative nu 1, 2 on E1, 0, negative nu 2, 1 on E2, 1 on E2, 0, and 0, 0, 1 on G1, 2. Normally, this is how you would have to sort of figure out this capital Q matrix by first doing Halpin psi, populating the compliance matrix S, then Q is the inverse of this. All right, so you can either do that on your calculator, or you can sort of calculate Q directly. There are equations that can calculate Q directly that are in the equation sheet, but the problem straight away gives us the in-plane stiffness matrix Q, which is super nice, right? You're welcome, students, for cutting down that work for you just a bit on the exam, okay? But okay, let's continue. We've got this in-plane stiffness matrix Q as shown below. The angle between the fibers and the x-axis is 40 degrees. A strain gauge rosette placed on the surface of the lamina aligned with the loading directions provides a strain state here. So what they're saying is there's a strain gauge rosette. This is a strain gauge rosette. Maybe you've seen these in your mechanics and materials class. If you're in the experimental mechanics class, you've definitely seen this. But it's basically a series of 3 strain gauges that all kind of form 45-degree angles with each other that you can stick onto the surface of a material, and it can measure strains for you in those 3 directions. And using the strains that that gauge outputs, you can determine what are the strains in the coordinate system aligned with the rosette. Now, if we just place this rosette directly on the composite as you see here, it would sort of sit like this, and you'd get measurements sort of in this direction, in this direction, and in this direction, which happen to be like the x direction, the y direction, and the shear gamma xy. Unfortunately, those strain measurements don't line up with the fiber direction, which is running 40 degrees with, like the x-axis, okay? So the problem says, all right, we put a strain gauge on there. We're getting these strain measurements. This is in microstrain, or this is in true strain, sorry. And then it asks, what are the stresses in the principal material directions given those strains that we've measured from that strain gauge? Okay, so let's go ahead and take a look at this guy. First thing that we want to do here is we have 2 pathways that we can sort of follow here. The first pathway is probably to transform this strain vector into strain in the 1 and 2 direction, and then use this stiffness to determine what the stresses are given that strain. That's probably the easiest method. The other method will be to transform the stiffness matrix in the 1-2 coordinate system, which is the stiffness matrix that you see here, into a stiffness matrix in the XY coordinate system. Then take strain multiplied by the stiffness in the XY coordinate system to get stress in the XY coordinate system, then transform the stress from XY into 1, 2. That is much more complicated and much longer, but it is another way that you could go. I'm going to go with route number 1. So I'm going to write that strategy down here, and then we're going to just go ahead and execute that. So the strategy here is to transform strains in the XY coordinate system to the 1, 2 coordinate system. Okay? And to do that, we'll use the following equation. Strains in the 1, 2 coordinate system are equal to, don't forget this is going to use the T star matrix now. T star times strain in the XY coordinate system. Okay, so that's the first step. And then find stresses with stress in the 1, 2 coordinate system is equal to the stiffness matrix Q times strain in the 1, 2 coordinate system. Okay. So kind of important to know that the stiffness matrix here that's given is the stiffness matrix in the 1, 2 coordinate system, right? So the principal material stiffness matrix. Principal coordinates, remember we talked about that last time. Principal coordinates are the 1, 2, 3 coordinates, all right? It's the principal material directions, the principal material coordinates. Okay, so let's go ahead and execute. We'll first kind of start with transforming the strains. So here we're going to need the T star matrix. And I'll remind you what that looks like. This is right from your equation sheet. This is m squared, n squared, mn, n squared, m squared, and negative mn. And we have negative 2mn, 2mn, and m squared minus n squared. Where remember that m is cosine theta. For us, this is cosine 40 degrees. And n is sine theta. So for us, sine 40 degrees. Make sure your calculator's in degrees if you're going to do this, not in radians. That's a common mistake. Don't make that mistake. So I believe that you guys could punch this in. You can figure out what your transformation matrix T is. I'll just write it here for you. 0.587, 0.413, 0.492, 0.413, 0.587, and negative 0.492, and to round it out, negative 0.985, 0.985, and 0.174. All right. So these are our values that go into our T star matrix. Remember, you got to use a T star matrix because we're dealing with strain here. And note that the T star matrix is not symmetric. I've seen that mistake quite a bit as well, right? These entries here are not the same as these entries over here. We have a lot of symmetric matrices that we work with in this class, so don't make the mistake of saying that the transformation matrix is symmetric, because it definitely is not. That has to do with rotation right-handed versus left-handed. But that might be a little TMI. But okay, now we want to execute strains times this transformation matrix. Okay, so let's go ahead and do that. So if I want strain in the 1, 2 coordinate system, it'll be epsilon 1, epsilon 2, gamma 6. This is going to be that T matrix. I'm not going to write it again. T star, excuse me. And oh, I'm sorry. We want the stresses. My bad about that. No, we're transforming. Yeah, this is all good. Times. Oh, geez. We want. My fault about this. We want X, Y, Z. No, we want 1, 2, 3. Jeez. This is correct. We have these guys. Okay, my bad. All right. So after doing this, you'll find that the strains in the 1, 2 coordinate system are going to be 0.0172, negative 0.0071, and 0.0348. Okay, so this is in 1, 2 coordinate system, right? So these are the strains that we would have in the 1, 2 coordinate system, the principal material coordinates. Okay, now look at the stresses given these strains. All right, and the stresses pretty simply are going to be the stiffness matrix, that capital Q matrix, which is above. It was given. My bad. My microphone just decided to crap out there for a second, but we're back. Stiffness matrix Q times the strains that we found, which is epsilon 1, epsilon 2, epsilon 6, which are these guys here. And so we have all of these things. You could punch this in, calculate this, and these are the stresses that you would find. 905, negative 39, and 166. This is an MPa. Okay. So nothing to it. You just got to know the steps. Again, there's this flexibility to transform from XYZ to 1, 2, 3 of the stiffness matrices, the compliance matrices, the strains, the stresses. You just got to know how to execute. And then transform from stresses into strains using Hooke's law. So that's that. That's the first example. This is a very common thing to do in practice, right? Is to take a strain gauge, slap it onto some apparatus because you want to know the stress state, measure the strains in that strain gauge axis, and transform it into axes that are more appropriate for the material, right? Sigma 1, sigma 2, sigma 6. So that's that. All right, that's example number 1. Example number 2, and this came from a previous final, so very representative question. Let's look at example 2, and this is an example actually from the notes itself. So let's pull that in here. I'm just going to bring this whole thing in here. It's going to be a bit big, but we'll deal with it. All right. This comes right from the notes, anisotropic part 2. This is slide 29. A thin tube is made of unidirectional carbon fiber with an epoxy matrix. So here's a picture of it below. The tube has an applied torque applied to it. So you see the capital T there. So this is the applied torque. And an internal pressure. So this tube is somehow pressurized with some internal pressure. So maybe we're just looking at a small section or a small segment of this particular tube. Determine the stress state on the surface of the material in principal coordinates. So again, we're looking for the stress state in 1, 2, 6. Given that the shaft has internal diameter of number, outer diameter of number, and unidirectional fibers that run at a 45-degree with respect to the longitudinal axis. Okay, so this thing is probably made by filament winding, and you can see that, you know, the fibers are kind of wrapping around what looked like it was a mandrel, and then they pulled it right off the mandrel, and all the fibers run at this 45-degree axis to 45-degree angle to this like long axis of the shaft. In practice, you would not really ever make a composite this way because, you know, you don't want all the fibers necessarily running in one direction. So typically you'd wrap a little bit this way, and then maybe you'd come back over the top of that and wrap it with like a minus 45-degree angle. That's much more common. But for demonstration purposes, this is a good example to sort of understand what's happening here. So if you need a little extra time, you can pause the video. Otherwise, I'm just going to go ahead with it. Okay. So what's our approach here now? Well, this tube, we've got some torque and some internal pressure. And you got to think back to like your combined loading from your mechanics and materials class. I know you hoped to never hear that term ever again, but unfortunately, it's back. So we can understand that torque is going to lead to some shear stress, and that internal pressure is going to lead to some normal stress in the tube. So what we want to do is we want to sort of figure out, all right, if I looked at like a little 2D element on the surface of this particular piece, what stresses would I see in that particular coordinate system? And then how can I transform those into principal material coordinates? So here the strategy is to populate the stress matrix sigma x, sigma y, tau xy, because these are the natural coordinates of the tube, right? So we kind of see this like xy coordinate system of the tube itself, and then transform to sigma 1, sigma 2, sigma 6 using the T matrix. Right? Bang. All right, so let's go ahead. The trickiest bit is actually populating this matrix here. So let's take a look at that. You got a 2D element on the surface. It's going to look a bit like this. And we got those fibers that run at this 45-degree angle, right? Okay. Now, if we're looking at that particular element, and hopefully this is not bringing back nightmares for mechanics and materials, you could possibly have stresses in the x direction, stresses in the y direction, and shear stresses. Tau, x, y. Okay? So remember how we define these. This is the x face x direction, and then the shear stress x face y direction, so on and so on. Okay? We have coordinate systems here that are natural to the system that we have, x, y, and then the principal material coordinates that we want are 45 degrees from that. So this is the one direction along the fibers and the two across the fibers. All this sort of makes sense. All right. We're told that we have a torque that's applied here that's 20 kilonewton meters. This is going to lead to a shear stress, tau xy. More on that in just a second. And then we have an internal pressure, P, which we're told is 3 MPa. All right, so it's a pressure vessel problem and also a torsion problem. So that's two forms of loading, a couple different types. And so we have to sort of remember what our pressure vessel equations are and what our shear stress from torsion equations are. All right, so let's go ahead and take a look at those. I'll remind you that a pressure vessel we're going to have a stress in the x direction, which is an axial stress. Sometimes you might see it as axial if you're working on pressure vessels. And this looks like capital P R on 2T. Okay? Where P, this is the internal pressure. R, this is the outer radius of the tube. And T, this is the wall thickness of the tube. This is a thin wall pressure vessel estimate. All right? So the pressure here is 3 MPa. The outer radius of the tube, sorry, we need an inner radius here. Inner radius of the tube, if we go back up, we're told that the inner radius is 190 millimeters, or inner diameter. So d inner is 0.19 meters. That means the internal radius is 0.095 meters. All right, so we want internal radius here, my bad, 0.095 meters, and divided by 2 times the wall thickness. Okay, don't make this mistake. If the outer diameter is 200 and the inner diameter is 190, that means the wall thickness is 10 millimeters divided by 2. Okay, don't make this mistake. Right? So this is 200 on the outside, 190 on the inside. Then each of these wall thicknesses must be 5 millimeters. Okay? Got to be careful with that. This is 2 times 0.005 meters. And so we get a stress in the x direction, if you punch all this in, 28.5 MPa. Can do a similar thing for the hoop stress, the hoop direction, which in our case is the sigma y direction. So this is, you might see this as hoop stress or transverse stress, or sometimes it's just sigma with a little theta underneath it. This is PR on T, and this happens to be twice the axial stress. And so you can just multiply this 28.5 times 2, and you'll see that this is 57 MPa. Lastly, we need our shear. This comes from torsion. Hopefully you kind of remember the shear stress from torsion equation. This is TR on J. TR outer this time on J. Where T, that's the torque that's applied, RO is the outer radius, and J is the polar moment of inertia. The shear is pi on 2, R outer to the fourth, minus R inner to the fourth. I believe that you can punch all these things in. The torque is 20 kilonewton meters. Let's just write it all out. Why not? Outer radius, this is 0.1 meters, 100 millimeters. And this is pi on 2. R outer to the fourth is 0.095 to the fourth minus 0.0. Sorry, I got that backwards. It's outer minus inner, so 0.1 to the fourth minus 0.095 to the fourth. This is going to be meters to the fourth in the denominator. And so you get a shear stress tau xy, which is going to be 68.6 MPa. All right. So that's probably the most difficult part of this is brushing off your mechanics of materials a little bit. Remember what's the pressure vessel equation, what direction is the axial stress, what direction is the hoop stress in our little coordinate system, what's the shear stress from torsion, those sorts of things. Okay. So finally, we can sort of use our composite knowledge now where we're doing transformations. And we have that the stress in like the 1, 2 coordinate system is equal to the transformation matrix T times the stress in the XY coordinate system. I'll just write it all out here. Sigma 1, sigma 2, sigma 6, which is tau 1, 2. This is the transformation matrix T. Our angle of rotation is 45 degrees, so you could figure out what the transformation matrix T is using all the m squares, n squares, etc., etc. I'll just cut to the chase and get it in here. This is 1/2, 1/2, 1, 1/2, 1, -1, -1/2, 1/2, and 0. And then our stress vector, we just sort of populated this. Sigma x is 28.5, area 57, and then our stress from shear, 68.6 is MPa. All right. Punch all this in, and you'll get your stress vector. This is going to be 111.4, -29, and 14.3 MPa. And that is my answer. So there we go. A little bit more application-focused examples here. We're looking at a tube that could be pressurized, that could have some torque applied to it. Very common situation. Have to understand, all right, if I have the stress in this particular XY coordinate system, what are the stresses in the sigma 1, sigma 2, sigma 6 coordinate system? Now, why would we want to make this transformation anyway? Well, we haven't quite gotten to that in this portion of the class, but I'll say that we use those values for failure criteria. We haven't talked about failure criteria yet in this class, but we're going to very soon. And so when you think about isotropic materials, what failure criteria do you think of? You think of Tresca's criteria. You think of the von Mises criteria, the maximum energy, distortional energy criteria, things like that. Those theories use principal stresses like sigma 1, sigma 2, sigma 3. You just looked at the von Mises equivalent stress for homework number 5. Composites have a very similar feel when it comes to their failure analyses as well, except composites don't use principal stresses. They use stresses in principal material coordinates, which are this like sigma 1, sigma 2, sigma 6 values. So the first step in analyzing whether a composite's going to fail is understanding what are the stresses in the one direction, the fiber direction, the two direction, the direction across the fibers, and then the shear stress that's applied. So you have to be able to analyze the stress state from one coordinate system, XYZ, into material coordinates 1, 2, 3, so that you can understand if that particular material is going to fail once we get to failure criteria. Okay, so that's going to be it. Kind of kept it relatively short. You didn't get a full lecture, but maybe only half an hour or so. So that's it. I'll be back as normal on Thursday, and we will see you then. Thank you. Bye-bye.